We're currently in the gas laws chapter, Unit 3, Section 2, discussing gas pressure. One of the very important things to note is the behavior of gases within a container. So if, for example, we had solid carbon dioxide, dry ice, let's go back to that for a moment. If we had dry ice, and we imagined that it would sublime. Sublime, of course, means that it goes from the solid to the gaseous phase without passing through the liquid phase. Would it then fill up a room by expanding into really large molecules, taking up all the space of the container? That doesn't seem right because I've never walked through gas particles that were so thick it was like soup. All right, let's look at hypothesis B. Would all of the gas collect at the top of the room? That doesn't really make sense because I know when I breathe air, it's everywhere in the room. Would the particles only hug the walls of the container? Again, I notice that when I breathe, the air is throughout the room. Finally, hypothesis D makes more sense because gases disperse and spread out throughout a room. So hypothesis D is more in keeping with how gases fill the space of a container. This is just a picture to compare densities of various objects. Notice that air has a very small density compared to metal, such as this iron anchor. And so when you compare the density of air, notice this helium, or air within water vapor, or even water vapor in the air here. So you can see that air has a tendency to have a very, very low density, or gases. We talk about air pressure as a weight that is pushing down an area of space. So for you to feel 1 atmosphere pressure is to say that there are 14.7 pounds pushing down on every square inch of your body. We of course don't feel that because we are used to it. However, if the pressure were to double to 2 atmospheres, you would definitely feel the 14.7 pounds exerted on every square inch of your body. It's kind of like when you dive, when you go diving, you feel that added pressure in your body as you go further and further down in a pool or in the ocean. This is a picture of how gas particles fill up in your tire in a car. You do notice that when you push on a car tire, it takes a lot of force to push on it, and you're feeling what gas particles are pushing back against you as you push on the tire. So, tire pressure. Boyle's law is a relationship between pressure and volume. So P and V are inversely related. P times V will always give you a constant. And as you can see from this curve, the more you lighten up on a syringe or you take the pressure off the syringe, then that syringe volume increases. Did I skip one? No? Okay. The next section here would be Charles' law, where we compare pressure and temperature. So when you heat a pressurized container, it actually gets more and more pressurized. That's why they say never to throw a canister into a fire. It could explode and it's very dangerous. And this is a direct proportion. This graph shows a direct proportion between temperature and pressure. As one increases, the other does as well. An example problem allows you to look at the relationship between perhaps pressure, temperature, and volume. Well, let's see, this particular gas, they're asking you to solve for a new pressure when the temperature increases and the volume stays the same. Because the volume of the gas stays the same, we're going to assume a rigid container. Okay, so we're going to cross out the volume since it stays the same. We don't need to worry about that in the equation. However, this is a pressure-temperature relationship. We know that from the formula, P over T is equal to a constant because they're directly related. As the temperature of a canister increases, the pressure is going to also expand. So we should see a rise in the pressure. We have to convert the temperatures to Kelvin, so we'll go ahead and do that. This first one would be 287 Kelvin, and this one would be 307 Kelvin. Now, we could go ahead and solve for the constant first by using this information. So it would be K equals 2 divided by 287. And that adds up to 0.00697. Right. We can take that, K, and set it equal to the right-hand side, so P2 over the new temperature, which is 307 Kelvin. Now solving for P2, we multiply both sides by 307. .307 on this side cancels, so we have P2 is equal to 307 times 0.00697, which adds up to 2.1 atmospheres. And this clearly shows that your pressure did increase, which makes sense. These gas laws, in order to fully understand them, you must be able to look at what is going on at the atomic or molecular level. So when we're talking about volume and temperature and pressure, this one here talks about keeping the temperature constant. So this is constant. So therefore we must be looking at pressure and a change in volume. Looking at that, we know PV equals K, meaning they're inversely proportional. Therefore, we can see that as the pressure increases, that would be the piston is being pushed down, the volume is going to get smaller. The pressure increases. Why? Because these particles, each particle now has less space to move, but however, its collisions within that area is going to be more frequent. So that explains that increase in pressure. If we look over here, this one appears to be talking about a change in temperature with a change in pressure. So we can go to the math algorithm. We know that P divided by T equals a constant, which means this is a direct proportion. We can try to explain the pressure increase once again by the increase in collisions. So in this one, the temperature is going up, so it's going to supply the molecules with more energy. That means that those molecules are going to be moving faster, so their frequency of colliding with the wall has increased, thus increasing the pressure. Makes sense, right? For combined gas law, we have to remember that the relationship is P times V over T is equal to a constant. So we can go ahead and solve for a constant using the initial information. So P is 2.5 V is 7.5, and T is 293. That constant works out to be 0.064. Then, with the new conditions, they want to know the new pressure, P2, when the volume is 10 and the temperature rises to 315. So then we can set that equal to K, which is 0.064. So, bringing this problem over here, P2 times 10 over 315 is now equal to 0.064. Right? 10 divided by 315 simplifies to 0.037. .0317. So P2 times 0.0317 is equal to 0.064. Dividing both sides by 0.0317, we end up with P2 as equaling 2.0 atmospheres. Check to see if this makes sense. Well, your container expanded, so that may ease up on the pressure, even though the temperature rose. This one's harder to tell because you have two things going on at the same time. Difficult for you to check to make sense. But you can always plug your 2 atmospheres back in to see if you get the same constant that you did initially for the original conditions. Finally, cloud in a bottle. If you recall doing the experiment, you want to make connections with the experiment and the actual weather conditions. So you notice in this weather map that when you have low pressure, there is precipitation. That's when you get your snow and rain. When there's high pressure, it's sunny. So this makes sense with the cloud in the bottle, because when you squeezed it, you actually recreated high pressure. And when you squeezed it, it was clear. And when you let go, when you released your pressure on the bottle, you created low pressure, which caused the moisture in the bottle to create a cloud. So this makes sense. High pressure is clear, low pressure is cloudy. Okay, we're done for today.